And howdy, welcome to Thursday. 2 weeks to go, actually less than 2 weeks to Halloween. My kids are not as excited as they were when they were younger, though. In high school, they still like to go out a little bit in high school. My oldest high schooler is not really interested in much of anything right now. So. You may not be able to tell it from what we've got here, but we're actually introducing the concept of counting. I know you've never done that before. Oh wait, you probably have counted before. But we're going to go through the idea of counting, some of the ways that we combine information that we have to get more information, and we'll look at some of the applications that we have for counting. It essentially forms the foundation of pretty much all the statistics that we do and probabilities and other things like that when it comes to anything that's discrete, like a population of people. You know, if you're trying to say, okay, what's the likelihood of somebody having AB positive blood? That's done through counting. And we're going to get to probabilities not next week, but the week after? Yeah, the week after. So next week will be permutations and combinations, both with and without and with repetition. With repetition is kind of boring. And then after that, we'll get into discrete probability, which is looking at what you can do with a large with a population in terms of trying to figure out what's going on. But it's all based on the idea of counting, and we'll try and get into some of that sort of thing. So as you can see here, we've got a product tool. I've got two things on the product tool here. In particular, this was just saying how many combinations can you have with a particular lock, since there are 40 numbers, 0 through 39, 64,000.
Oh, so this is a different product rule from taking a derivative, right?
Yes, different product rule. This is a counting product rule versus the derivative product rule versus I'm trying to remember. I was looking for images and couldn't find much of anything. And there was another thing that came up that said that counting or the product rule for, and it was like, oh man, must be product rules for everything. The other thing here is looking at combinations of outfits. If I had, like, I don't wear skirts, but if I did, how many skirts do I have? How many blouses? How many sweaters? How many combinations of outfits could I have if I was going to do that? And we'll look at that as well. And then the other thing over here is just a nice picture of, no, actually it's not, it's Pigeonhole. Our other topic is the Pigeonhole Principle, and we'll be talking about that and what that means in terms of how we look at populations. First, a word from our sponsor. So we'll have a quick review, we'll get into counting, and then we'll be talking about the Pigeonhole Principle, or pigeons. Kind of tongue-in-cheek. Hopefully you have raincoats. I did not bring any for demonstration, just so you know, so it'll be I don't want to clean up afterwards. Any of you guys ever been somewhere where they had a lot of pigeons? Like big cities in the east? Probably. I don't know if California does or not. I don't recall my time there. But there are a lot of places in the east where you'll walk out and there'll be pigeons in mass, just kind of wandering around looking for something to eat. Have you seen Home Alone, Lost in New York? Like the lady there with all the birds? It's literally that way in some places. I've seen pictures. I need someday to get to London, but I've seen pictures of the pigeons on these statues in the little parks in London, and I think that would be kind of interesting to see. Before we talk about divisibility, when we're introducing the idea of number theory and what we have to go to work with there, here given two integers a and b, where a is not 0. So a is the one that's not 0. If b divided by a is an integer, in other words, it's actually a whole number, it doesn't have any fractional part, and it's an integer value of some sort, then we say that a divides b. It's kind of the opposite. If b divided by a is an integer, then a divides b. Yes?
I think it's kind of funny, it's like, if b line a, then a line b.
No, that is not true, not from divisibility. Just because A divides B does not mean B divides A.
Well, I'm not saying like they're the same line, it's just like a different kind of line.
Oh, different kind of line. Yeah, I've got the divide. I made sure it was a slanted line as opposed to the vertical line. As you know, this uses a vertical line, which is the same as a bitwise or. But we could say B is. If I had it on this slide, yeah, I do have it coming up down on the next part. The way we write it is with a vertical line, but we can say B is divisible by, B is a multiple of, or A is a divisor or factor of, and factors are something that we also got into last week. Some examples, you guys tell me which ones are and which ones are not. Is it a case where A is divisible, is A divides B or A does not divide B? So does 8192 divide 1024? Yes. So 1024 divided by 8192 is an integer. Yeah, no. So that's the key thing when you're running through your exam or your quiz and you see a larger number on the left with the vertical line, and we're talking number theory, so the question is about divides or divisibility. If you have a larger number, it's not going to divide. It's not, because the larger number is never a factor of the smaller number. Not when we're talking about integers. 13 divides 169. Yep. In fact, 169 is 13 squared. 11 divides 132. 11 times 12 in this particular case. 5 divides 927. No, because we've got a 0.4 left over. So it's not an integer value there, it doesn't evenly divide it. I guess another way you could say it would be that B modulo A is equal to 0. So if you really wanted to be strict here, we can test this. So we can test it with the modulo function. It's just one of those things that we're actually able to do. Another thing that we looked at was the division algorithm, which is not an algorithm. It's just kind of a description of the idea of how we can relate integers to each other. For any two integers where one of them is positive, in this case A and D is a positive integer, there are unique integers, a quotient and a remainder, such that A is equal to D times Q plus R. So with the restriction that R must be between 0 and D, but not equal to D, and that then gives us the unique results. There will never be more than one Q, and there will never be more than one R. So there are unique numbers, and it defines a relationship. We use this as a basis for modulo arithmetic, which we use for encryption, we use it for hashing, we use it for preventing overflows in numeric values, all kinds of stuff like that. So let's put some numbers here and see what we get. Anything, well, okay, something maybe less than 5 digits would be good. Man, tough room. Let's do 47, this one can't be negative 47, we'll go 3. So now the question is, what's Q and what's R? Because they have to be unique. in this particular case, 3 times 15 would be 45. 3 times 16 would be 48. And since I have a negative value here, my quotient has to be 16. Why does it have to be 16? Why can't I put 15 there? Well, let's try it with 15. So if I have negative 15, that gives me negative 15 times 3 is negative 45. My remainder, the thing that I have to add to it is negative 2. But that breaks my rule here that remainder has to be between 0 and D. It can't be negative. So as a result, 15 is not the number we want. We want negative 16, which gives me negative 48. And now I can add a 1 to it. So R is equal to 1. So you have to be careful here. D must be greater than or greater than 0, and R has to be greater than or equal to 0. And be careful. 0 must be less than or equal to R, must be less than or equal to D. D is positive. So that's really our only kind of, or actually, positive? Yeah, D is positive. So what would happen if A was 0 and D was 3? I should put that on there. Let's try 0 and 3. So my quotient, 0 divided by 3 is 0, and my remainder is 0. Not too hard, but it's just following through. I don't remember which. Oh, it was actually my 2810 class where we were talking about stuff. It's one of those things where don't fight it. When it comes to math, a lot of times the formula rules. So you don't always have to understand all the things behind the formula, but you do need to be able to apply it. So when I homeschooled my son, I made him cry a couple of times because I said, you really don't have to understand why that formula works. You just have to be able to apply the formula. I don't even remember. Oh, it was we were working with fractions, and he was having issues with that. But yeah, my kids suffer because I've tried to help them and do stuff like that. I learned I could never be an elementary, junior high, or probably even a high school teacher. I just don't quite have the patience for it, even with my own kids. But the other thing that we learned was that our operations on computers don't necessarily operate the same way, in particular because we do allow for negative values for the D there. And as a result, we can have a remainder that is also negative. So just understand that on a computer, you may not get, your results may vary on a computer, is I guess the way to put it. We use it for hashing, encryption, modulo arithmetic. Modulo arithmetic's used in encryption, as well as some other things. And modulo arithmetic is really not that difficult. It's just having an operator computing something and then doing the modulo operation at the end. So if I have 531 plus modulo 7, where the plus operator is a modulo operator, 11, then I do the addition, and then I do modulo 7, and I wind up with whatever my result is. Now, I was looking at this last night. I've actually had this slide for a little while, and I don't know how I ended up with a result of 0 for this, but somehow I did. And that was obviously not true. When I looked at it, I said, no, 530 or 542 is not going to be divisible by 7. Because the 500 would have to be divisible by 7 for that to be true. Anyway, got some other things here. As you can see, we're looking now at positional numbering systems. Luckily, we no longer use Roman numerals. I had to look up something, and I was doing a crossword, which I hated crosswords for a long time, and then I finally started doing them maybe 5 years, maybe 10, maybe 7 or 8 years ago. And I've discovered that there are times when I don't actually hate them, but I did have to look up the Roman numeral for 500. It's a D. What? I don't. I knew C for 100, M for 1,000, I for 1, V for 5, L for 50. I didn't know 500. I read somewhere that there are seven symbols, and I guess I don't know them all. Ones, fives, tens, 50s, hundreds, 500s, and 1,000. So yeah, that would be all 7. So if you want 1,000,000, that would be 1,000 M's. So obviously you couldn't do really large numbers with Roman numeral system. So we use a positional numbering system, and we do that. As you can see here, I've got binary, I've got decimal, I have base 5. I've never seen a system that uses base 5, but we could do that. We could do octal, we could do hexadecimal. The key thing here is that each position is based on the base that we're using raised to some particular power. So if I'm representing a floating point, a float being a real number, then I might have a fractional value. And in that case, we represent it the same way. It's just that at that point, we've got a little bit of additional information going on here. Get rid of this stupid thing. It's amazing how many things you copy from one slide presentation to another, and then you kind of forget. That's going to change everything. I'm just not worried about it. I'll fix it later on. So here, the key thing here, I don't have it. When you get into that's why I saw it from my other slide presentation where I said, I took so much time to do this and I copied it. In decimal, what's the dot called? Decimal point. Decimal point. We could call it a binary point. We could call it a trinary point, a quaternary point, an octal point. It gets kind of old calling it a point, whatever the base is, point, because it means the same thing. The actual term for this is the radix. And really, it just means that non-negative exponents and these are all negative exponents. So the radix kind of becomes an inflection point where everything goes from positive, big positive, down to 0. And then the radix tells us where we start getting negative exponents, or where we're dividing by the power of the base raised to something. And then the things here, this just becomes some digit from from 0 to b minus 1. So if I've got base 53, then I've got to come up with 53 symbols, 0 up through to whatever represents 52. And that would be the symbol that I use here, and then that becomes the value or the coefficient that I use down here if I want to express this as a polynomial. Yeah, it is for this class that you have to do the polynomial. If I want to do the fractional part, all I then have to do is start doing my sequences with, you know, a plus a minus 1, b to the minus 1, plus a minus 2, b to the minus 2, you know, etc. And I just add all those together. So we can express it as a polynomial, which is a, we haven't decided to get rid of the 2899 exam. We are looking at things we can do. So you guys are still looking forward to a 2899 that you have to finish to get your associate's degree. We'll see where it ends up in the long run. Conversion, basically, when we do conversion, I don't think I have it on the next slide, but let's say that I want to do, let's choose an interesting number, like 19, nice prime number. So what I do is I do a modulo. I have one side for the quotient, or pardon me, the div, where I divide by 2, div 2, and then I've got a modulo 2 over here. So 19 modulo 2 is 361. Nobody's listening. Mod 2 is a 1. Div 2 is 9. In other words, 9 times 2 plus 1. It becomes the quotient and the remainder, essentially. So I do the modulo again. I get a 1, or I can subtract the 1. And I get an 8 over here. 8 divided by 2 is 4. 4 modulo 2 has a 0, or I subtract the 0. And then I divide by 2, I get a 2, 0, I get a 1, and 1 divided by 2 in integer terms is a 0. So this becomes 1, 0, 0, 1, 1. Base 2 is equal to 19 base 10. So we just do the modulo and the division. Modulo, division, modulo, division, modulo, division. And you can, we can do integer division, or we can subtract out that value and then do the division. So it becomes 18 divided by 2 after we subtract 1. 4 divided by 2 after we or 8 divided by 2 after we subtract 1. Whatever works for your brain. But it's an alternating, and this is the, if you look at a study guide, have you guys ever looked at any of the study guides for the 2899? Yeah, sometimes they're a bit confusing, but this one's listed at, understand, you know, you can alternate modulo and division in order to do a base conversion. We could go the other way if you were good at binary arithmetic in your head. I'm not that great at it. I can do addition, multiplication. I have to do long form, so it's too much trouble. So to do the conversion the other way, we can just look at the base in the position, or the exponent value in the position, write out the polynomial and figure the result. The other thing that we can do is we can cheat here, and we can start with the leftmost 1 bit, and we add that to our result, and then if there's a bit to the right, we multiply by 2 and add that one. If there's another bit, we multiply by 2 and add that one. Multiply by 2 and add that one. Multiply by 2, add that one. There's no bit to the right anymore, so we're done. Yes. Oh, just rubbing your eye. No questions, just pain. The other thing that we looked at was primes. A prime is a number that can only be divided by itself in 1, meaning that there are no other integer values that can be multiplied together to come up with a prime number. Every integer on the planet can be factored into a set of prime numbers. Or actually not even a set. If you're going to factor it, or if you're going to get the factorization, it's not a set because you can have repeated values. If you're going to factor it, you're only finding out what prime numbers you would need to multiply together, but not how many times you have to multiply them together to do it. So here, prime factors, the list of prime numbers without repeats. In other words, it's a set, and then the prime factorization is a precise list of all the primes, including any repeats that you happen to have in there. So that's kind of the thing we're looking for. 49, prime factor is 7. Prime factorization, 7 times 7. 72, prime factors 3 and 2. Well, we've got 22233 for the prime factorization. So that's the idea, is we list all the numbers with repeats for the prime factorization. Another way to write this, and oftentimes you'll see it this way, is 2 to the third and 3 squared. This is becoming difficult. There we go. Hold on. What's that? I must be pressing down too hard. 3 squared. So that's the other way to do it. And what we would do is we would say, well, I'm multiplying 2 cubed times 3 squared, or 9 times 7. But the other thing you run into is that I can have two numbers that have the same list of prime factors, but don't have the same prime factorization. Like 9 and 27. Both of them have 3 as their only prime factor, but one of them has 2 3s, the other one has 3. Or, if I make it 81, now I've got 4 3s. Same set of prime factors, but different factorization. Another one that we looked at was the greatest common divisor, Euclid. Several different ways to do it. My own favorite is to do the iterative one where you just subtract the value the whole time, which is probably what he did. They said, oh, this one fits in? Okay, let me subtract the smaller number from the bigger number and see what I get. And subtract it again and subtract it again, because addition and subtraction are fairly easy. If we were to look for that, let's see. Is something like this. Actually, he did more than one algorithm, but you never know. Oldest numerical algorithms in common use. Using here's the subtractive algorithm is simply this. Where you rinse and repeat the inner loops as long as A is not equal to B. So while A is greater than B, C is equal to A minus B, A is equal to C. So I keep subtracting B. Otherwise, if B is greater than A, I subtract A from B. So I do those inner loops until A and B are not equal. And then when they're equal, I'm done. A or B, it will equal 1, and then there is no greatest common divisor, or whichever one is greater. And that's going to be your greatest common divisor. I actually have a different version of it. Rather than having two loops inside another loop, I just use one loop with an if statement that will swap the values. Because it doesn't really matter what, are you using A or B as long as you keep them correct in what you're looking at. So. Yeah, modular arithmetic is the way most people do it. I really like the subtraction, because subtraction, it can be done about 32 times as fast as the modulo and division. So just so you know, those are the kinds of things that you can look at. Maybe Weebly has something interesting. Version 1, I've got my while loops there. Here's the if. If A is greater than B, A is equal to A minus B, otherwise B is equal to B minus A. So I've got an if inside a while loop, and I just keep going through. And in the end, greatest common divisor is A. Well, B is not equal to. So learning how to read algorithms can be kind of interesting, but that's the thing that we do. So given two integers, A and B, A times B is equal to the greatest common divisor divided by the least common multiple. This is, if I remember right, it's theorem 5 from the textbook. That's the one that I reference you guys to in order to figure out what the least common multiple is. The only other way I know of to get the least common multiple is through factorization. So you factor everything, out everything until you have common terms from each one, and then you multiply the prime factors. So counting now, counting down till the weekend. We still have a day. What do we count? We count how many people are online. There were 4, I don't know if there are 4 now. Count how many people are in the classroom. There are 4 of us, including me. So there are more students online than in the, you count how many people are in the building. You count how many classes you have to take. You count how many dollars you have to spend to go to a restaurant that you'd like to go to. Everything that we do, we count. As I was growing up, I had my sister, my oldest sister, I didn't realize this until my mom mentioned, yeah, we always have to get everybody the same number of presents because my oldest sister always counted. I didn't realize that, my mom did, so she always made sure that we had the same number of presents. But the idea is that counting becomes the basis for many of the other things that we do in life. For computers, it gives us an idea of the complexity of a problem. You know, how big it is, how hard it's going to be to solve. Those are things that can be very important in terms of trying to determine what we're going to do with the problem. We also use it as a basis for probability and statistics, especially with populations, with people. If I go out and I've got to find out, okay, how fast is this virus spread? This is something that we did 3 years ago. Then the question becomes, all right, how many people have become infected out of a population of a specific size? And then we do that computation or that count over a period of time to try and predict what the infection rate might be, or the R factor, I think, is what they call it for. I'm going to have to go back. COVID is only, it's a bad memory. You try and forget what some of the things are, but it's basically if one person gets it, how many people are they going to infect? So that is all done by counting. That forms the basis for all that sort of thing. Usually the things that we're counting, well, actually, I don't know of any time when the things we're counting doesn't come from some set. The set of possible outcomes, the set of people, the set of cars, the set of whatever. Everything that we count comes from some collection of things, And if we know the size of things, then we can start saying, oh, 25% of the population actually, or I guess now they're claiming everybody has been exposed to COVID. I wouldn't necessarily guess that everybody has been infected. Well, I guess if you're if you carry carry it, then you had it. They say everybody's been exposed to it. I don't know. I never got sick. But the product rule is one of our first ones. It was on the cover slide here. The product rule, and this is the text definition of it, which is sometimes a little hard to understand. But it basically says if I have two tasks, and one ways to perform the first task, and then 2 ways to perform the second task, then there are N1 times N2 ways to perform everything. I don't know about you, for me that doesn't make a lot of sense. So I started to look at this in terms of how can we deal with this in terms of looking at the problem. So let's say, how many of you have built a computer? Yeah. So if you got the money, you got choices galore. You can go out and, I've got 400 motherboards I could use for this build. It's like, oh, how do you choose? Well, not all of us have a lot of funds, so we might hopefully be a little bit more limited, or we might say, okay, I'm going to choose a certain processor family, Intel, AMD. I'm going to choose a form factor. I'm not looking for a home theater, so I'm not looking at an ITX. I'm going to go for an ATX. I want to put it in a tower, and I want to, those are all things that we can do. Or it could just be our funds. How much money do we have so that we can build what we want? Let's say that we've got 3 CPUs. So I'm looking at the Intel i5 family, the 13th gen, whatever. We go forward from there. I've got 3 of them that I'm looking at. They've got their overclocked model, they have their not overclocked model, and they have their integrated graphics model. That's at least 3. But that's going to drive then our choice of motherboard and hopefully reduce the numbers that we're going to look at, but we might want features there. I want 2 solid-state drive, M2 solid-state drive slots instead of 1. So you might be limited at that point, and there might only be 2. Or, I've had really bad luck with, trying to think of a manufacturer that I don't like. I've had bad luck with this manufacturer, so I'm not going to look at their boards. Or I've had really good luck with, I like Gigabyte. I've been using Gigabyte now for 4 years, 5 years, in several different systems, and it's worked well for me. So I would go with Gigabyte, reasonably priced. You get some good features. You go from there. So 2 motherboards, 3 cases. Power supplies become an issue. You're going to have a graphics card or not. If you're going to have a graphics card, you want to bump up your power. Otherwise, you might be able to go under 500 watts. Your computer is, in fact, a space heater, if you think about it. So I might have 2 power supplies, the totally modular one and a semi-modular. Anybody know what I'm talking about? Yeah, a modular one basically has the power supply, and then everything becomes a plug that you can put in. The first build that I did was not a modular power supply, and it comes with this complete wiring harness, and you've got to figure out what to do with the wires you don't use. And you end up with a lot of them on most computer systems. So I'm really happy that they went to the modular system, where you can say, oh, I need some mole connectors because I've got an older system that I need to provide power to. So you get the mole and you take it to your Blu-ray drive or your DVD drive, and that gives you the ability then to only have that one rather than 5 different mole cables that you've got to hide inside your case. Graphics cards. I need to change the language on this. You can actually find graphics cards now, and some of them are even, if you're willing to go 1 generation back, you can get them at manufacturers suggested retail. So when I bought the stuff to build my computer, I did the Newegg Shuffle, which they're not doing now, but they put that together because graphics cards were going for 2 to 3 times their manufacturer's suggested price. And what they would do is the shuffle was an opportunity to sign up. And if you won the shuffle, you could buy the graphics card and maybe a motherboard. They usually required the thing you wanted and then something else. They would bundle those together and you get them at manufacturer's suggested retail price. So you're not getting a great deal. I mean, they could do it now and say, okay, we're going to give it to you at 20% off, which would be really nice, but they don't do that. But that was, you know, that was the thing when I actually put this in here. Like, okay, if you want to, I got a 3060 graphics card, and I probably saved about $400 because I got it that way instead of just going out and buying what was being sold. And then memory chips. Another option that you might have here. Oh, I want them with the LEDs. I don't want them with the LEDs. Frankly, I don't look at the LED as when I'm looking for options on things. I don't care if my computer lights up. I care if it goes fast and if I can do what I want to do. Anyway, so out of all of these things, how many computers can we build? Okay, what's in purple on the very first bullet? Pardon me?
225.
225? I don't remember right off the top of my head. But basically, you just multiply everything together. This is the product rule. Oh, I'm on the wrong screen. There we go. 3 times 2 times 3 times 2 times 2. So I've got 16 times mine. So 90 plus 54 gives me 144.
That's close.
I mean, the point is that it's more than like 4. Because you've got all these different options. It's one of the things that you run into. You go to a restaurant, you say, yes, I'd like the steak fajitas. Okay, you want churro beans, you want refried beans, you want, this. You want, do you want Mexican rice or, and they come out with like 25 different options for your side, your first side, your second side, your dessert, and other stuff like that. So it's all the product rule. Fast food restaurant, another one. 12 sandwiches, 8 sides, 6 drinks, 4 desserts. How many possible meal orders could you have? A meal, of course, would have to include everything there. So I want the sandwich, the side, the drink, and a dessert. Well, obviously then it's just 12. Really? For a really fast computer, sometimes it just doesn't. Now it doesn't. Now it doesn't. So I've got 12. Let's see if I can do this without times 8 times 6. I can't see anything here, so hopefully this is not too bad. 12 times 8, 96, times 6 is 540. Times 6 is 540 plus, let's see, 540 plus 36, so 576 times 4 is 2,006 there, so 2,003, yeah, I just lost it, 2,306, if I remember right. And so I'm just going to put it as an approximation here, 2,306. And I might see that eventually. Ooh, there it is. It's amazing, writing it, and it magically appears like 20 seconds later. What if we can have sandwiches only? Or a meal. So you can order your sandwich a la carte. What does that do to our choices? Does that alter how many meals we can get? If I just add the option to have a sandwich alone, does that alter the number of ways that we can order a meal? Yes, I'd like the meal with large fries but if I allow you to have the sandwich alone, how can I get that in here? Is it another multiplication thing? No. If I can have a sandwich by itself, that just means that now I've got let's see if it comes up. Uh-oh. I'm up here working hard, and it's not taking everything. Ways to have a meal plus 12 equal to 2,318. And if we allow no dessert with the meal, then what? It becomes another addition. So do you want do you want the dessert with that or not? So each time that we do that, we now have a different thing that we're doing. We're no longer multiplying because we're not providing combinations of things that we put together. We're instead offering alternatives that don't matter. So this would be ways to have full meals or sandwich only. Plus ways to have meal without dessert. Oh, that sounds so. Okay, let's see how long it takes this time. It may not do anything. Yeah, I thought I was doing. I'm not sure what I thought I was doing. That became. So yeah, it's connecting things weirdly. Actually, let me get my computer to think a little bit. I don't know if there's an update for Windows, but this is aggravating. And there's nothing I can do with this. So I'll just delete it. That's not what I meant either. I didn't know I could do that. I can actually convert, assuming that it can recognize my writing, which it obviously couldn't do in some cases here. There we go. So it'd be ways to have a full meal. Well, I will fix the slides because this is getting kind of hard to do. But anyway, the meals didn't change. The having sandwiches only didn't change, other than the fact that it dropped my 8 because that was on the line that went down here to the W that I managed to erase. And then if we allow no dessert, then it's just how many ways can you have a meal without dessert? Well, that would be our 12 times 8 times 6. So it's 1/4 of that, or the 576. So we add 576 to it. So now we've got not quite 3,000 ways to choose our meal when we go to like Arby's or Burger King or whatever. And that doesn't talk about the options on your sandwich. Hold the pickles, hold the lettuce. Special orders don't upset us. So anyway. We didn't multiply. Products aren't the only way to do things. The product rule is when the sets are not independent. In other words, I'm combining the CPUs with the case, with the power supply, with the motherboard, with the, they're not independent. I've got to choose one from each set in order to make everything happen. That would be a product rule where I'm combining them that way. So we have to choose one item from each of several sets that are describing our problem. For the sandwiches only, all we had to do was say, well, I've got 12 sandwiches. So we only added that 12 in. And then the same thing, if we said no dessert, it was, well, we had the number of ways to get the combinations together with the desserts, but if I take the desserts out, I still have the product rule there, but it's the product rule where one set is no longer considered. So I have, sandwich, side, and drink, or sandwich, side, drink, and dessert. And then you can choose which one of those, but they're added together, not multiplied together. So our sum rule is when a task can be done. This is the textbook again. It's talking about tasks or other things. And I can do it one of n1 ways or one of n2 ways. Then we add them together. For this one, I used to ask, I don't know if I've got it on my slide or not. Oh yeah, I do. Let's say that I give extra credit. And early in the semester I say, okay, here are these 13 topics you can write a paper on. Pick one and you'll get extra credit. And then, like, after the midterm or something like that, I say, oh, wait a minute. There are these other 20 possible topics. If you didn't like the first 13, pick one of these. Well, that doesn't multiply. I don't now have 13 times 20 because you're not going to write 2 papers. I'm only going to accept one for extra credit. So here, I've now got 33 ways to get extra credit. Write a paper on one of 33 topics as opposed to writing on one of 13. So that's another way to look at the sum rule, is if you're just adding options. It's like buying a car. Suppose you want to buy a car, first dealer has 15, then 5, then 7. How many choices do we have? We do not have 15 times 5 times 7. It doesn't work that way. So we just add them together, and I'm not going to write it down because you guys, I'm tired of it going on. Or you take your child to the store, and you wander around the store for the 3 hours that your child can stay there and look at the toys and try and pick something. And they narrow their choices down to, well, I want one of 25 stuffed animals, one of 15 board games, 5 Nerf guns, 10 dolls, 8 remote controlled cars, or 12 action Pokemon figures that I might be able to sell in 25 years for a major profit.
Very narrow.
Yeah. Well, it's a kid. And then you tell them, sorry, honey, or sorry, sonny, or whatever term of endearment you use, you can only have one. So how many things do they have to pick from? Well, you don't multiply these things together. They only get one. So it becomes one of the 40, 55, and 20, 75 things to choose from. So if they got 75 things to choose from, they can pick one. And that's all they get. So that's our sum rule. And another way, and this is leading into some other things that we need. Suppose we had an opaque ball or opaque bag with 7 blue, 4 red, 12 yellow marbles. How many times do we have to reach in the bag to get a blue marble?
We take the marbles out when we grab them.
In this case, we do, yes. Otherwise, you can't see what it is. And you don't put them back. Because assume that you put the marbles back. How many, is there a way to tell how many balls you have to pull out until you get a blue marble? No, it could be the first one. You might never pull one out. You might continually pull out a red ball or a yellow ball. So, or marble. You don't know. So, in this case, we're saying you reach in, you pull one out. How many do you have to get a blue? To guarantee that you get a blue. It's a variation on our counting. Let's say worst case. This is the kind of luck I have. As you can see, trying to clean a food processor's little thing. I've got 11 stitches here. Yeah. But here, my luck, I'm going to pull one out, I'll get a red one. I'll pull one out, I'll get a yellow. I'll get another yellow. I'll get another yellow. I'll get a red one again. Woohoo! And then I get like 4 yellows in a row. And then I get another red one. And then I get a red one after that. And then I get 6 more of those stupid yellow marbles. How many have I pulled out? Yeah. How many do I have to pull out until I can tell you without a doubt the next one I pull out will be a blue? 16. The number of red plus the number of yellow. So I have to ensure that I didn't pull out all the other ones first. Or that the next one I get is not going to be, it has no chance of being red or yellow. It's got to be blue. And then the next one I pull out is blue. So I've got to pull out 17 of them in order to make sure that it's not possible to pull anything else out. So I have to pull out 17 marbles to ensure that I've got one blue. This would be the kind of thing that you'd do in the middle of the night. You don't want to turn on the light and you're trying to grab something. You know, I've got whatever in here and I keep grabbing stuff, and I'm going to carry stuff out, something out the door. How can I make sure that I get the thing I want? Well, I just keep pulling until I know I've got one of the things that I want and not something else. If I remember right, the quiz question I had is talking about SOPs, or the exam question. We look at this as an inclusion or exclusion, or as a way of counting sets together. This is a formula that also will be important to you on some unnamed exam. If I have 2 sets, how can I calculate the cardinality of the union of them? Well, I add the 2 sets together and I then subtract the intersection, because the intersection occurs twice if I just add the numbers of the sets. Let's see. Now, pigeons. Everybody's favorite thing in the world. Pigeons, little things that coo and leave presents for everybody as they're flying around and doing stuff like that. Suppose you're going to school at Big U State, or Big State U. So it could be the U here, or it could be, let's see, anybody know how many students there are at Utah? Okay. The last school I attended as a student was Arizona State. At the time, there were 40, let's just say 40, or over 40,000 students total. But big schools can be really, really big. I think there are some schools out there now that have around 60,000 students. But let's say, it's Big State, but their U is small. So Big State U doesn't have quite that many. Let's say you're planning to live in the dorm. If there are 1,000 dorm rooms, how many students have to be in the dorm to ensure 2 students, at least 2 students are in the same room.
Is there a max? How many students to share?
No. But if I put 5 students in the same room, then at least 2 people are sharing the same room. So that doesn't affect this computation. This is another counting rule. If I have 1,000 rooms, how can I make sure that at least one room has more than 1 student? How many students would I have to have? What if I had 5? Is there any way to guarantee that at least one room, oh shoot, that's what's going on. I forgot to plug in my computer here. Now I can't see the plug, there it is. That's why it's been acting flaky, I forgot to plug it in. So how many students, if I've got 5 students, what can I do? I can put those 5 students I can put each one of them, I can give them a range of 200 rooms and say, okay, you can stay in any one of those 200, you can stay in any of those 200. They can choose their own out of the 200 rooms. Is there some way I can guarantee that no matter what happens, it's like musical chairs, at least 2 people have to be in the same room?
You just add one more student in there.
One more student than there are rooms. That's the only thing that's required. I have to have at least 1 more student. The number has to be bigger. So the way to guarantee it is to have 1,001 students, almost like 1,001 nights. What if all of them are in the same room? Then if I have 1,001 students in the same room, then I've got at least 1 room with 2 students in it. I don't know if there's a room big enough. I'm sure there is somewhere where you could put 1,000 people and they wouldn't necessarily have to be piled right on top of each other. But not in any dorm room I've seen. So, it's been a while since I've been in a dorm. All right, Pigeonhole Principle is basically that. And I'm trying to remember, the mathematician was looking at pigeons, and British people are kind of strange sometimes. I can say that because I'm part British. Goes back a ways, but somebody came from Britain. We use it for categorizing or sorting items, and the idea here is how can you guarantee that there's something in every category or every sort category that you're trying to do. If I have K categories, so I have some positive number of categories, boxes, pigeonholes, characterizations or characteristics of something, and there are more than K items, then there's at least 1 category, K, that has more than 1 person in it. There's like, for example, let's say that you were doing demographic studies and you were saying, okay, I've got ages 0 through 5, 6 through 10, 11 through 15. So if I break it out, if I go up to, old people don't matter, so anybody over 50 falls into 1 category, but at least I've got, 0 to 5, 5 to 10, so I've got like 10 up to 50, I've got 11 categories. How can I guarantee that I've got at least 1 category with more than 1 item in it? Well, if I've got 11 categories, I just need 12 people. That one may not be something that makes any sense to you. How about this? How can I make sure that I have 2 people born in the same month? One more than our months. 13 people, 2 of them are going to be born in the same months. What if I'm looking at people born in the United States proper, the states, not the territories? How many people do I have to know that I can have at least 2 people who are from the same state? 51, or as Barack Obama said, 58. He's been to all 57 states. He said, I forget what year, it was like 2012 when he was running. He said, yeah, we've been to all 57 states. I thought that was kind of funny. Anyway, to have at least 4 people with the same birth month, we can extend this and say, okay, well, I've got to have, I have to have enough people that there are 3 in every month. And then if I add 1 more, that means there's going to be 4 people like that. So, pollsters use this in order to choose how many people they're going to poll, in order to have some kind of measure where they're categorizing people and making sure that they fall into different kinds of things. Our general pigeonhole principle basically relies on this. If I've got n items that I'm putting into k categories, then I'm going to have the ceiling of n over k items in at least 1 category. For example, if I've got 49 people, then I've got at least 5 people with the same birth month. There's at least 5 people that are going to have the same birth month at that point. And the reason for that is the ceiling of 49 divided by 12 is 5. It's 4 point something, and with the ceiling, you just go up to the bigger value no matter what. If I've got 1,000 people, we know that there are 366 days of the year that can be named. The way that I can guarantee it is, or if I have that, then I know that at least 3 people are going to have the same day of birth. So 1,000 people, I say, okay, how many people were born on this day? Who knows? They could all be born on February 29th. I don't know. Maybe there's a convention or something like that. But I'm going to run into at least 1 day of the year that people would be born on. Might not be quite that interesting. What if I have 9,000 people born after January? Born after, on or after January, so born this century. Actually, there's arguments about whether the century began January 1st, 2000 or January 1st, 2001. A lot of people will say that 2000. So born in the 2000s. If I have 9,000 people, at least 2 people are going to have the same birthday, because how many days are there? Excel is nice. It gives you the ability to subtract 2 dates and get the number of days between them. There are 8,693 days, including January 1st and up through the 19th of October of this year. What's today? The 19th of October. So I'm covering myself here. I know that if I get 9,000 people in a room today, that 3 of them, 9,000 people, all born after the year 2000, that 3 of them will have the same birthday, at least. There could be more. Once again, I could have a convention of people born in 2000. Let's see, my oldest was born in 2002, so I could get all those people who were born in 2002. And at that point, I would have a few more that would have exactly the same birthday. We could probably even go down to hours. How many hours are there in a day? 24, so we multiply by 24, and anyway. Why do we care? Believe it or not, this is not just a simple activity for saying, gee whiz, there are at least, if I've got 9,000 people, at least, if I've got representatives from 179 countries, I may not have 2 from the same country. But if I've got 180, basically we use these for counting purposes in order to help us make sure that we meet certain criteria that we might need for randomness, for the properties that we're looking at for a particular thing. We also use it to determine probabilities. What's the probability that at least 2 people have the same birthday? Well, if I've only got 2 people, then it's going to be fairly low if they're completely random. The other thing that we do is, believe it or not, computer scientists like to model the world. We like to look at populations and other stuff like that, and we try and find ways to mathematically talk about the world and people and stuff like that. Anybody in here have Apple Plus? Have you watched or read the Foundation series by Isaac Asimov? No, Foundation's Arthur C. Clarke. Now I don't remember. It's either Clarke or Asimov that wrote the Foundation trilogy that then became the Foundation 5 books. And anyway, the thing there was that rather than modeling the world, he had come up with a mathematical way of modeling history by looking at what happens with large populations and the pressures and things that go on there. So, someday we may be able to do psychohistory, which was the terminology that they use for that particular model. It would be really neat if we could, for example, just model a small section of the world, like the financial system. There are people that say, oh yeah, we've got, actually I've heard, the latest one I've seen is, our AI model will choose your stocks for you. It'll be really, really good. Okay, maybe. We do need more counting tools before we get too much further along. And that's where we're going to be next week. We're going to talk about permutations and combinations. A lot of times it becomes rather difficult to try and just count something because the numbers are very big. So instead what we do is we come up with formulas to represent that counting mechanism. And that's really all that the permutations and combinations are. Is we're looking at what happens when you have a population and with permutations, you actually order things in it. So there's a specific order. It makes a difference whether I'm number 1 or number 27. That would be true with permutations. With combinations, order is not important. Combinations is, generally speaking, used just to put people in sets. So, you're going to go, I've got a group of people in the first car and a group of people in the second car. How many ways can I split the people between the 2 cars if the first one has 5 and the second one has 5? That's the kind of thing that you would do with combinations. It doesn't matter which car you're in, as long as you're in one of them, you're going to be able to go. All right. So now, lab time, questions, or early weekend. And it's not an early weekend for me. I actually have to teach tonight. Any questions, guys? Problems with programs? Okay. I promise you that let's take a quick look at the programming assignment. We do have a programming assignment coming up. It's on combinations and stuff. So you might be slightly interested in its performance. So we have a counting problem. For the homework here, not a counting problem, but for our homework, we're basically doing large numbers. And anybody programming in Java? I've had people, especially with some of the things that we have in the permutations and combinations, the next programming assignment, I've had Java people try and use the big integer library for it because we do run into some limitations there. It's not worth it. It's just, if you want to spend the time to do it, I'm not discouraging you. I'm telling you it won't make any difference in the way I grade your work. So I'll say, good job, you looked up big integer. Did you get the answer that we're expecting? So the question is one that you need to answer. So let's take a look at our homework. Essentially what we're going to do is we're going to look at what happens when we start putting big numbers in. And to do this, we're going to use Fibonacci again. On Canvas, I've got a text box for you to fill things in. Just write down the results for 40, 50, 40, 45, 46, 47, and 48. And then a 1 or 2 sentence explanation of why you see what you see. I think I gave you the, Windows executable, I give you a C program and Windows executable, so if I download this, I've got it on my computer somewhere, but we might as well. Here, save that, we'll go to the directory. Terminal. Here, /HW, oops, 8, no, not 6, 8, WC. Okay, enter a positive integer greater than 1. So let's say 40. 490. Okay, that one came back pretty fast. N for no, anything else for yes, let's do a Y. And you'll note in my example code how to clear the input buffer. If you're mixing characters and numbers, sometimes it can be an issue. So I've got a method in the C++ code there. 45, not bad, we're still looking at 1,135,000,000. So let's do 46. 1.8 billion. 47. Negative. Negative? What's negative?
Overflowed space.
Yeah. So that's what I want you to do is write your program or run this program. Ask you. Write down the results for that. Short explanation of what you're looking at. The C++ program should actually work for it. 20th Fibonacci, so 5 is 5, 10 is 55. Yeah, so I've got the right stuff going on there. But that's the homework assignment. And I do that because as soon as we get over here, sure as shooting, somebody's going to try and figure all of this out, and they're going to run into a problem. Let's see. How many ways? Print out the formula because the number is too large. You can do it with the big int or big integer in Java. I'm not asking you to do that. You probably do for permutations and combinations want to use long instead of int. If you're doing C++, if you're doing Java, you can do long as well. C++, you can try long, but I don't think Visual Studio or the G++ compiler actually implement 128-bit integer, which would be what you would need to represent the number. So just keep in mind, all you have to do is how many ways can doctors be selected from the first set, how many ways can nurses be selected, and then how many ways can I get the first dose. So this one's looking at a hospital that's trying to inoculate people against something like a COVID or something like that. You don't want your emergency room people to be down at the same time. So what you would do is you would go in shifts. You'd say, okay, I've got 12 doctors, I'm going to take them in thirds. So that way I've at least got 2 shifts I can cover rather than 3. So and then I'll do the same thing with my nurses. So that's what we have, 12 doctors, 36 nurses. We're going to break it into 3 batches. That way if somebody has a reaction, we're not down, or if some set has a reaction, or if it takes 5 days for them to get well after the shot, we've got that built in. So how many ways can I select the doctors or the nurses? And then how many ways can I administer it to administer that first set of doses? And then do the same thing for the second set, which would imply the same thing. How many ways can I give it to doctors? How many ways can I give it to nurses? And then I have to combine those. What rule should we use at that point? We haven't left behind what we're doing today. It's either going to be the product rule or the sum rule. I can tell you right now, in order to determine the number of ways I can give it to a set of doctors is going to be either permutations or combinations. Same thing for nurses, permutations or combinations. So are we going to add those, or are we going to multiply? That's the question you guys have to answer.
For number A, is that just 12 choose 4?
Yes. But the question is, what are you choosing them for? And is it permutations? Permutations of 12 things taken 4 at a time, or combinations of 12 things taken 4 at a time? Same thing for the nurses. Combinations of 36 things taken 12 at a time, or permutations of 36 things taken 12 at a time. And then after that, to get the total number of ways, do I do addition or do I do multiplication? We'll talk about it. But think about it. Does the way I choose doctors affect the way I choose nurses? Or are they completely independent? Is it like these motherboards accommodate the CPUs I'm looking at, the power supplies accommodate them, the graphics cards work with them? Are they independent that way and I'm choosing one from each set? Or are they build on each other? Like I said, it's either the product rule or the sum rule. And then finally down here, the total ways that I can give it to the staff would be, how can I give the first dose, how can I give the second dose, and how many ways can I give the first, how many ways can I give the second, and then how many ways can I give the third. I'll give you a hint on this one. Once I've chosen how I'm giving the first and the second, the third is always only just one way. It's whoever's left over is going to get that third dose. So if I've chosen the first and the second, the third doesn't matter. Whatever's left over. And we'll take a look at that one next week with combinations and stuff. And what will drive it home is stuff like this. How many ways can bonuses be distributed? Well, if it's 1,000, 600, and 400, or 2,000, 1,600, and 400 for 23 employees, I'm sure hoping I'm getting the biggest bonus. So it's different. The order, if I'm selecting 4 people, the order is important at that point. Am I the 2,000, or I'm the 1,000, or the 400? As opposed to this, everybody gets 1,000. At this point, it doesn't matter. Am I first or am I fourth, as long as I'm one of the 4 people. It doesn't matter which position I get. One of these is combinations, one of them is permutations. And the other thing is just to make sure that you have test values, print out the permutations of 35 things taken 12 at a time and combinations of 23 things, taking 11 at a time. The output that you see here is my sample solution program. What you'll do is you just put your formula here. I'm not going to put the formula in. The numeric answer is this. You can't represent that with an int. You can't represent that with a long. It goes negative on you. We get overflow, and at that point we say, let's just put the formula here. We know how to figure it out. We just can't at this time. So you can compare your answers to what's here. These are not here to mislead you or anything. This is and this program is probably the only one you'll write all semester long that has no input. So I'm not asking you to have to type stuff in. You can't, no, please don't. I need to start adding this. Please make sure that your interface matches this. In other words, I just run your program. Because I usually use scripts to grade programs. So if I give you a sample, that's how I'm expecting the input to look like. And if yours doesn't match mine, like one of the big ones, like when I ask ordered pairs, two numbers on a line, no separations, no commas, no anything else, please do that. With a function one, for example, there are people that will ask me to put in, f of 2 is equal to, and they want the letter, the parentheses, the number, the parentheses, the equal sign, and then something else. I'm going to curse you in the 20 minutes that it takes, or 20 or 30 minutes it takes me to get my input script ready to test 6 cases like that, because I really don't want to type it in, especially with an owie on my finger. So, the typing, I don't have a number pad anymore either. So yeah, don't do that. Don't say, do you want to do it again, if I don't ask you to have a menu that asks if you want to do it again. There's just no real reason to do that. The point that we're trying to get is the number sizes that we're looking at, the ability to compute permutations and combinations. With this one too, the other thing, I haven't put it in here. I thought I had, and I need to add Python in here as well. So Python is a valid option here. Please do not use factorial. In help session next week, or at the end of class next week, I'll go through a way to do the permutations and combinations without using the factorial function. The reason for that's really simple. If I'm trying to compute a factorial, then what I'm doing is I'm multiplying all the numbers, for example, from 1 to 47. I then would not be able to use 47 in a combination or permutation calculation because it would cause issues. It's overflow. You saw that. It goes negative. Even with longs, those numbers start causing issues after a while. So instead, we're going to do permutations the way that we as humans do it. And I'll show you that next week as well. Anyway, guys, have a good weekend. Kept you here long enough. You have places to be, coffee to get, or your favorite drink from Starbucks or whatever. You guys online okay?
Thank you.
See you. Have a good weekend.
Thank you.
You bet. Have a good weekend.